presenter is Yan. Her topic would be similarity-based appearance prior for feeding a subdivision match in gene expression images. Or
yeah, actually, I think the title a little bit. My name is Yan. My advisor is Professor Kakayaris. So today I will present a method to fit a subdivision-based mesh atlas using discrete macro random field. So the problem that we want to solve is to fit a subdivision-based mesh onto an image. Mesh is a powerful tool which can model the geometric structure like the curves in 2D or the surfaces in 3D of an object. And the mesh, what we work with is the 2D, the planar mesh. So a standard approach to compare different images which are composed on different subjects is to bring them to a common space or coordinate space, which is known as the atlas. So the atlas is built, for example, for the brain. When we fit it on different images, this means we locate the mesh vertices so that it can model the boundaries, for example, of the geometric structure of the object of interest. And fitting subdivision-based mesh atlas has been applied in different applications. For example, in the top image, it is used to register multiple images, mouse brain images in gene study. And on the left figure, it is used to track the segmentation of left ventricle in real time. So the problem stemming from the application point of view in our work is to register mouse brain genes expressed image. In gene expressed image, the intensity signal is corresponding to the expression strength of a certain gene and at a cell position. And given gene expression images, the biologists want to compare the patterns, the expression pattern. This means like the intensity patterns in the same corresponding region of interest, like the two yellow region here. This is the keys to study the functional networks between different genes. So genes images has been collected. So an automated method that allows us to find the correspondence between different images in a few number of images is very important. And subdivision mesh is an effective tool to do this because subdivision mesh is a fractal-like process that allows you to draw the smooth curve like in the rightmost figure. Just based on the very relatively few number of points on the right figure, you can see that. So at the consist level, the base mesh is very close and not really fit the regional boundary of the objects. Like here is of the mouse brain, but when it goes to higher subdivisions, it can delineate the boundary. Here is the subdivision mesh at subdivision level 2. So today I will present our approach. We have two contributions. The first is a method for fitting the subdivision-based mesh, and the second is the prior we incorporate to improve the accuracy of this method. Those two contributions are from two recent publications. Actually, the first in the first I got the second one, but I want to present both of them here because you will have a complete idea about this method. So let's start with an illustration example. I think it's very difficult to see the image, but like here it is a gene expressed image. And we start with an initialized mass. So for at each iteration of mass evolution, we want to find the new position for each quantum point, which are the points at the consist level. So our approach evaluates samples, some candidates, and evaluate all the possible previous possible candidates, and move the quantum point to the best one. Here we can see that this boundary fits better. In this example, we just so like when we move one point with the assumption that each point move independently. And in our formulation, a fitting solution is a configuration of a set of displacement labels for each quantum point f here. So each f1 to fn, each fi is the displacement label for the quantum point I. Like here, the displacement is corresponding. It also helps us to infer the position of the new candidate. And because the number of displacements at each step is discrete, so that's why we will see the discrete macro-random fields here. This label assignment problem is solved using a discrete macro-random field where an energy function E f given image, the test image I, which is a weighted sum of geometric energy and appearance energy due to the limitation of time. So in next slide, I will focus on the appearance energy here, the country in the second, and also in gene expressed image. This is non-trivial to incorporating appearance because of its complex appearance. So in the top row, the hippocampus region is shown in a blue boundary. Look at the top row, you can see that the intensity pattern of the same region vary a lot across images. In this image, this means the gene is expressed very weakly. And look at each column, we also can see that in gene expressed image there is a lack of visible F field for anatomical reason. In this, it is very difficult for us to see where is the boundary. So, because of those changes in gene expressed images, we cannot compute. I mean, when we evaluate the fitness of a mass on the test image, we cannot compute the appearance features just based on the test images. That's why we introduce a similarity-based appearance trial. So here, the appearance trial, the appearance features compute an image patch around a mass per text is defined based on the similarity degree between this patch and the patch around the corresponding quantum point on the test image. We can do this because of the existence of a red initial state image, which is a special one, which it is generated in a special way so that it inhibits the anatomical reasons information, and also it is most similar to all of the other images, gene expressed images. So somehow we can, when the biologists manually annotate the reason boundary, we also can look at this image and based on the shape file or something like that, draw the boundary. So in this way, we also follow this to do the manual annotation and do the same thing. However, because in most of the region the gene expressed image have very weak intensity information, so we don't want to include the vertices where they are not reliable, and therefore we also introduce a system method to identify the appearance the vertices which have appearance consistent across like different images, like from the training based on training data. And here in this figure, the vertices with the warmer color has the higher consistent degree in appearance. And this is the qualitative result of three methods of fitting the subdivision based on gene expression image. The two last are our work, and in the first method is in the first method the author is modify iterative or closest point approach. The second method is when we use MRF, and the last method is when we use MRF with the appearance of prior, the similarity based appearance prior. And here we two first, the blue are the results of boundaries, and the red are the unnoted boundaries. So the arrows here indicate the boundaries where our methods improve or have noticeable improvement. Like when we put this, when we incorporate the appearance, it fits better. Also, yeah, in other region like that. And this is the quantitative results when we compare the overlap of our result boundary with manual annotation using dice coefficient, dice similarity coefficients, and the statistical test shows that our methods, the second method is better than the first in 4 out of 14 regions, and the last method is improved 6 when compared with the second method. So I have presented our works about fitting a subdivision based mesh. And the below is our publication to the reference. If you have any questions, yeah, please feel free. And thank you so much for the attention. Yes.
So you're applying Markov random fields to solve the problem?
Yes.
What other people in the field that are doing the same kind of work used to solve the problem?
This application.
Yes.
Yes. So previous there are two approach for the gene expression image application. One is the registration, the normal registration, image registration, and specifically for the subdivision mesh fitting. There are 3 or 4 previous methods. This is like the latest results of them. In this method, they use modified iterative from this point. They based on they detect the boundary, outer boundary of the mouse brain.
Why do you believe your method works better than the other? What's the secret?
Yes. So the results are like why this is better.
Yes, but why it is better?
Oh yes. So in this method, because with gene expression images, it is very difficult to incorporate the appearance information of inter-regional region here. So in previous method, either they just use the outer, they fit the mesh just based on the outer boundary of the mesh, and yeah, using based on the shape trial imposed in the mesh. So the inner is not really fit well. This is the first, and in the lattice method, they incorporate the appearance in a regional region, but based on just using yeah. So they change different classifier for the quartz and see like whether the quartz on the region varies move to the left or right, up and down, something like that. However, we can see that like in this the quartz, the size of the quartz are maybe very small at higher subdivision. At lower, it is not transferable, but when at higher resolution, it is very small and maybe not like statistical just something like that. And also here, but yeah. So let's move on our method. But in our method, we instead of finding like when we move the boundary, we evaluate each possible configuration. So we don't find like, okay, so where is this point? But we will say, we will answer to the question, this point here is good or not, something like that. And our method also, because we also provide a method to just the reliable points, but it also improves the accuracy of the regional boundary.
Thank you.
So I probably missed that, so can you explain how you get the mesh first?
So the mesh is another word.
Okay.
Yes. So they built this specifically for this application. So we just have the mesh. We have the mesh, and we need to
But in order to get that mesh, you already have the boundary, right?
Pardon?
In order to get that mesh, you already have the boundary information.
To get the mesh, you mean
right.
To put the mesh on the image or to build the mesh? So to build the mesh, then
so the mesh already have the boundary information.
Yes.
Okay.
Yes. Yes. I mean the mesh has the boundary information. Actually, it has the boundary cost they call the crystals, and yeah. So they are already annotated, so that's why they call it the mesh atlas.
Okay, thanks, Yang's presentation. The next presenter is Pranav Mehti. And when scoring for a presenter, if you have personal relationship to that presenter, please select yes in abstain from voting. Thanks. And each presenter has 10 minutes to answer the question. Thanks.
Very good morning. My name is Pranav, and I'm working with Dr. PhDshowcase in the quantitative imaging lab. And we're working on a video surveillance project, and the title of my talk is Modeling Human Behavior for Video Surveillance Using Geometric Constraints. So today we're going to go through a quick introduction, and then we're going to see how we can build geometric models for using in real-world video surveillance applications. And then we'll try to build what is called an accessibility distribution, and then we look at some experiments and some results. So what is surveillance? Surveillance is basically defined as observing changing behavior. And we use this, it's usually regarding people, and we use this observations for predicting their behavior or managing people. This is a simple Google search for the word surveillance. it's from the Google database, and these are the top results. As you can see, at least 90% of these images either have a camera in them or are the output from a camera, like a camera video. So I guess at least as of today, we all can agree that cameras are going to play a very significant role when it comes to surveillance. So now we have excellent cameras, HD cameras, we have excellent displays, but and the next step is to automate video surveillance. Now what is automated video surveillance? Automated video surveillance is basically being able to automatically detect events that require attention. Now if you consider a real world scenario, like an airport, there are going to be a lot of cameras, and then that display of the geometry of the location of the camera. He knows the environment where the camera is located. Now this information will give him cues regarding predicting the human motion. So if he sees a subject moving in one of the cameras, this person will be able to predict where the person is going, or he might be able to predict in which other video he might be able to show up. Now so this information comes from the person's understanding of the geometry. But today's video surveillance applications do not have access to the 3D geometry of the building. So the question we started asking was, what if a surveillance system has access to the geometry of the building it is located in? How do you leverage this information to write better surveillance applications? So we started off with building a geometry model of a building where a camera is located. Well, we started off with the PGH building. We simply take the floor plans, and almost all buildings these days have floor plans like CAD diagrams that give you the measurements like length, breadth, and height. Now you can use this information to build geometry models, 3D models using Google SketchUp, Maya, and Blender. Now what you see on the right is a 3D model of the PGH building, and what we do is all of these allow us to export it in a file format called Collada. Collada is basically a worldwide interchange format for 3D information. It allows us to store 3D information, basic graphic element information like 3D geometry, mesh information, lighting information, camera information. And the best part is this Collada has an SDK which allows us to access the raw information. And once you have the raw information, you can simply render it using OpenGL and use it in your applications. Now what you see over here is a rendering from the OpenGL of one of the floors from the building. Now the next question is, now we have a 3D model. But in real world buildings, there are cameras in the cameras. Now how do you embed a camera in a 3D model that is equivalent to a camera in the real world? So how we did that was we inserted our object in the real world, and we also inserted the same object or constructed the same object in the 3D model. And we rendered the 3D model, and we tried to register them. Now basically this simply translates to taking the 3D model and doing a series of transformations, a translation in the rotation, and then doing a perspective rendering of the image. Simply you're changing the view so that you get the view of the camera. Now at this point all you do is you simply extract what is called as transformation matrix, which basically embeds the information regarding translation and rotation. And this can be stored in your Collada file. Now at this point, with a click with one button, you'll be able to change the view in your 3D model, which simulates a camera in the real world. Now the next question was, we have a 3D model and we also have cameras in them. What we wanted to know was, is there a distribution to the floor or the location where the camera is present? Do people tend to access certain parts of the floor more often than the other? So, that is the model of the floor, and we can break that into small triangle meshes using dynamic triangulation. And what we did was we take an extended video, and every time we detect a human, we simply project him back into our model. And we use simple statistics to build what is called accessibility distribution. Well, here the accessibility simply the detections are taken and they're simply thresholded into two classes, one being accessible and black being not accessible, less accessible. So now the question was, we were able to build this distribution because there was a camera. The camera was giving us information regarding the distribution. So the next question we asked was, how do you build a distribution at a location where a camera is not present? Now, so in order to answer this question, what we tried was, maybe if I'm able to associate the point on the floor with some features, and I'll have a prior then, and I'll have the features of that point. Now I can use this to train a classifier. Now at that point, all I have to do is, anytime I have to find the distribution for a new geometry, I just have to take the new features, throw it into the classifier, and it'll spit out the distribution for me. So, but what features? Well, clearly from the previous slide, we can see it has something to do with the distance from the walls. So obviously the features have to encapsulate the information regarding distance from the walls, but also it doesn't, a human really doesn't, is not worried about a wall that is a mile away. There's a restriction towards observation. So we looked at what is called as theory of proxemics. Theory of proxemics basically it segments the physical area around a human being. It is an observational study, which basically observation study regarding how humans make use of physical space around them. So it segments the space around him into intimate space, personal space, and social space. So and also all interactions in closed hallways happen in the social space, which is about 80 inches or something. So we use this information to build what is called as the standard features. So now we have the standard features and we have the prior distribution. And we trained a classifier, and we started trying different geometries of the edit. So this is the floor of the fifth floor, and these are the results from the classifier. This is only 2-category case. You can see how towards the center it's more accessible, and away from the center it's less accessible. And this is for the 3D geometry. You see how it works even in curved places. And we took the next step simply using 4-category cases. So here we were red being more accessible to black being less accessible. And these are the results for the 4-category case. Right now what we're trying to do is, there's more than one way to calculate features. You can calculate them from the feet at a certain angle, or you can calculate from the face. So we are not completely sure what are the best features, or what is the best classifier. I mean, what is a more suitable classifier for this application. So we're trying to work on an experiment that will actually help us benchmark these distributions. So once we have this distribution, the idea is that maybe given a human's initial parameters like his direction of motion and his velocity, maybe we'll be able to predict his motion based on this distribution. And yeah, this is most of what I have. If you have any questions.
How many other people are working on it? Is there a team here? Do you have one part of the project? Or like?
But this one's, I'm working on this one. So.
Okay, so this is a one-person project, right? And you're working about either.
Where can this thing find application? I mean, the usage in building space. How can we use it in
well, if you consider a scenario like an airport and there are multiple cameras, and if I see a subject in one camera, and if a person has to locate him in another camera, if you consider an application where there are 250 cameras or 2,000 cameras, and if you have to go through 24 hours of video, that's a little time consuming. But maybe if you're able to predict his motion, even in places where there's no camera, you might be able to locate the video quicker.
But
simply
what you have shown me here today is not this.
No,
what I'm saying is basically usage of building space.
Yeah.
So this is probably your next step.
That's the next step, yeah. Maybe given how we will be able to do that.
So regarding back to the current state, regarding this usage application you developed, where do you see this finding benefit? I mean, how can we use this information?
The distribution?
That certain parts of the building are used more than others and so forth. That's what you have constructed so far.
Yes. Well, this is the idea is that given the distribution, and if I have the initial velocity, I might be able to see into where the person might go based on the distribution, where it's more likely to go. And that will actually, the idea is basically to predict it.
I understand, but that's your next step, right?
So this is the beginning step for that.
Yeah.
So
Do you have any applications in mind for the beginning step?
Maybe scenarios for huge population where you expect huge crowds, you might be able to set up barriers or something.
Maybe in building management, because that shows you what parts of the building basically are ready to be used. So. And building is a capital investment, so building managers and big buildings want to make use of this information.
Yes, sir.
What motivated you to use neural networks?
Well, it's only one classifier. We need
Right.
to
Why did you choose that one and not another one, for example?
well, to start with, it was we started off with using a 12-dimensional feature vector, and we needed something that is not linearly separable. So we thought that was a good idea.
Okay, thanks for the presentation. And the next presenter is
good morning, everyone. My name is Ahmad Thomas, and my advisor is Dr. Barbara Chapman. And my job will be as a biobase for analysis and efficacy applications. The outline of my talk will be as follows. I'll start with the motivation and related work, followed by talking about the different area analysis techniques and the methods that have been implemented in our research compiler, which is called OpenMesh. Later we'll talk about our integrated system and the tool that we have developed to display the array analysis information. Last but not least, we will conclude our work and give some future things. The motivation behind our work can be categorized into these sections. We try to identify and fix inefficiencies in defining interprocedural and static arrays at compile time. We reduce data movements between host and GPUs while using some directed PhD programming models that support uploading a portion of arrays from CPU and GPU and vice versa. Our tool can serve as an enhancement to the auto-parallelization module in different modern compilers. And finally, we enhance the user's ability to analyze the code. As a motivation example here, we can see that this array A is a double-dimensional array with 200 elements in each dimension. For the invocation of P1 in this loop, the first 100 elements in each dimension have been defined. On the invocation of P2, the rest elements in each dimension have been used. So our tool can show the portions of these arrays that have been accessed with the associated access mode. We have defined 4 access modes in our tool: diff, use, and formal, and pass for the formal and actual parameters. Additionally, by using a PGI accelerator module, we can define one region in each function. So instead of porting the whole array in each function, we can just port the specific portions that have been accessed. We have defined a term called access density, which can be depicted in this formula. It illustrates the number of references for each portion per access mode, divided by the bytes allocated to that particular array. And as we can see in this example here, for example, the portion from 10 to 15 has been used twice. So we can see here, and since the number of bytes allocated is 20, so we can see that the ratio, or the access density ratio, is 10, and our tool can display this thing. The related work is categorized based on our motivation. PGI accelerator and for all compilers exploits array analysis to reduce data movements. CAP, which is the compiler-aided parallelizer optimizer, automates the insertion of compiler directives using array analysis. Different tools such as PAPI and Docofile records hardware counts of data, but they operate at the low level where arrays lose their structure. And finally, Prism was previously developed in our group but it didn't support array analysis. Now let's define this term, the array region analysis. Actually, it's a technique to summarize a subregion of an array that is encrypted by a statement, sequence of statements, or loops. And the importance of array analysis can be as follows. It's essential for cache behavior and hierarchical memory machines. It's also fundamental for array characterization and generation computation in distributed memory machine. It also can enhance the auto-parallelization module since auto-parallelization doesn't support the analysis of procedures that are being called inside loops, in contrast with our tool that can show this information. We have 4 main techniques for array analysis. The first one was the classic method, and actually it doesn't have any kind of summarization for arrays. It analyzes the array as a whole and doesn't give any information about the regions that have been accessed. Primitive-based and linear-based are 2 methods that support summarization, and the linear-based region method was implemented in our compiler. It depends on the subscript of arrays to construct some linear equations that can be solved, and it's more accurate than third computation because it can handle some non-rectangular shapes. And the last one is reference-based, which is the most accurate one because it maintains information about all references to each element in that array. But this is on the account of the storage, which is needed. Our integrated system can be depicted here. We have extended the ITA phase inside our compiler. 2 modules have been extended, the array region analysis module, and we combined it with the high-level intermediate representation, which is called zero in our compiler. We extract the lower bound, upper bound, stripe, and a comprehensive report about the attributes of each axis arrays and store them in a region file. And we have developed this array analysis graph using Qt application framework to extract the data or the information in this file and display it to the user in a tabular format. To show our array analysis tool, as we can see, it supports syntax highlighting. Here the X symbol represents the global arrays, and here are all the functions inside our in the application. And as we can see here, we are showing a simple example, and we have a grep method. We are searching for an array group AA. Once we click on the find button, all the accesses to this particular array will be highlighted. As you can see, this array is added in this file. It has been defined twice and used 3 times. It's a 1-dimensional array. The lower bound, upper bound here is shown with the stripe, with the data type, with the number of bytes, the number of dimensions, and the memory location with the access density that I've mentioned before. Once we complete our application, we need to use some specific flags to generate some files. The extension for these files .gn and .rgn. .gn represents the polygraph. Once we load the polygraph by invoking our tool, we will load the polygraph. As you can see here, each node represents a procedure, and these edges represent the polygraph relationships. And as you can see here at the bottom, once we click on this button, view array region analysis data, we will be able to display the array analysis graph. Another example here to show the usefulness of our tool. We have this array, which is a formal parameter, that has been used in this function, this procedure. It has been used 4 times. It's a 1-dimensional array. And as we can see here, without parsing the whole code, we are showing that it has been accessed the same region from 1 to 5. by verifying that there is no dependency among these loops, we can do software transformation to merge these loops together to improve data locality and reduce the parallel overhead generated from defining two parallel OMP parallel regions instead of one. And another example here is about the global array in the NASARIO benchmark. It has been used 110 times. It's a 4-dimensional array with these dimensions. And as we can see here, we didn't access the whole like array in this particular file. So using a directive-based GPU programming model, such as PGI accelerator, we can just define these portions in each dimension that have been accessed. To conclude our work, we employed the interactive tool to find the hotspot portions of integer arrays. We show that this information can be critical for memory and cache utilization, and we reduce data transfers between host and GPU. And our tool has been tested on some FBC benchmarks. The future work, we are trying to combine array analysis with data dependency to automate checking dependencies among loops. We try to extend our tool to support analysis and visualization in the of remote area accesses in the partition global address space context, such as the CAF core array reinforcement programming model. And last but not least, we try to enrich our tools with a 3D visualization module. And thank you very much.
Have you done something other than the LU example?
Yeah, the DT and the LS for the support C++ and the Fortran.
Yeah, can you give a short explanation of your goal? What is the goal of
The goal of my work is, actually, in each aspect of this work, it can be extended. So the goal of my work actually is to visualize array accesses, because this thing has never been done. Usually the compiler can do some analysis, such as array analysis and data dependency, but without any visualization. And as we know also, the analysis done by the compiler is limited to the analysis of the compiler. So if we show these accesses to the developer also can have his or her own part in the analysis. So this is one main thing. Another thing is to improve data locality by showing like these accesses, plus supporting offloading portions of arrays using some directive-based GPU programming models, because most of them now support offloading portions of arrays. So instead of porting the whole array across the GPU, we just need to port like the portions that have been accessed.
Does your method work better with respect to competing methods?
True.
Does your method work better with respect to competing methods?
To competing method? What do
You
you mean?
presented a method that does something.
Now, it depends on the analysis, it depends on the this method, region method, I mean the region method. This method has been implemented in our compiler, so we have extended this method. So we can say that we are restricted to use this method. Now, as I show in that diagram, it's kind of like coming in between. It's not very efficient because it's for summarization, not as the classical methods, but at the same time, it's not the most accurate one because it doesn't give information about all the
Can you
elements.
show the slide that shows exactly this information?
Here.
So what is this?
Here we have 4 techniques: classic, triplet based, such as regular sections, linear based, such as region, and reference based, such as the atom images. So each one of them has its own analysis, but X patterns. They vary in terms of accuracy and The classic methods, as I mentioned, they consider the array as a whole. So they just use 2 bits, and only 2 bits needs to be stored. That's why it's very efficient. But as far as the accuracy, it's not, because it doesn't give any information about the regions that have been accessed. In contrast with these 2 methods, the triplet and the linear base, they support summarization, but as I mentioned, the linear base is more accurate because it can handle some complex arithmetic operation. The last one is the reference-based. It analyzes each axis, or all it maintains information about all the references to each element in this particular array. So it's the most accurate, but on the account of the storage.
I understand.
Yeah.
And this is a nice qualitative description. My question is, do you have any quantitative proof in numbers? How much this method is better in this respect with respect to
No,
the other?
because we are restricted to, as I mentioned, to this method in our compiler. So we just extended this method.
I think, I mean, you gave a nice presentation on that, but the research problem is not clearly defined. I see that you did a nice programming exercise and then you showed that certain regions can exploit the GPU, but I don't see too much research. So what is the research problem, and then what is your specific?
Actually, now, as I mentioned, one
it's fuzzy. Your contribution is fuzzy.
Okay. Now we have maybe like 2 main things now. The first one is to improve cache utilization by improving data locality. This is one thing, and we need to combine our array analysis module with a data dependency module to automate checking dependencies among the different tools. We can do that, and we can also show the dependencies on a region basis instead of the regular method like to check dependencies.
So is that a new algorithm, or is an optimization of an existing algorithm?
No, we need to develop this thing. Because, for example, the module in our compiler now supports dependencies among each loop, not among different loops. So what we need in our is to support the dependencies among different loops, to show the dependencies among regions, not among specific elements. So this is one thing. And the other thing is also there's a programming model, it's called Courier Fortran, which is a partitioning global address space programming model. It's supported in our compiler. We try to mix our work with that work to distinguish the remote accesses from the local accesses, and by doing that we can save too much execution time. Yeah. So
Perhaps in the slides, yeah. I should have been in the slides. Thank you.
I have one last question. Do you have any ground truth to evaluate your method?
He said that he does not have
regarding the methods.
Yeah, how do you compare your method? Is there some gold standard that you can compare to?
Now maybe I can.
Can't you annotate or can't you
Maybe
manually
I can refer to previous research using those methods. This is like the only solution. But as I mentioned, we are working on our compiler. We are restricted to this method in our compiler. We have extended it.
I understand that, but can't you manually analyze some data and then see
Using the compiler.
see how your compiler does compared to the manual analysis?
Now we need to implement these methods first.
Oh, you haven't even implemented?
The methods, the other methods.
No. I'm talking about just your method.
To implement
Just your method, you can create gold standard data yourself.
Yeah, for example, I took some experiments with GPU programming, and I found that okay, we saved up to 30% of the execution time. 30%.
3%.
Yeah, by floating only portions of arrays instead of portions of arrays. Yeah. So I'll this one.
Thanks, Aman. Thanks for your presentation. And next presentation is GPU accelerated interactive visualization and planning of neurosurgical intervention by Mario. And please, all presenters, keep your presentation and question in 10 minutes. Thanks.
name is Mario Lincoln, and I work on the computer graphics and interactive media lab. I do 3D computer graphics, GPU computing stuff, and my top two aids are automatic application. And so for some surgical procedures, such as biopsies, the neurosurgeons need to insert a straight axis tool, such as a needle, from some point on the surface of the tool to some target point within some region of interest within the brain, such as a tumor or something. And for inserting that needle, the neurosurgeon's job is to minimize the risk involving the whole procedure, right? And they need to consider a number of things in order to minimize the risk. First, they try to get a pathway for those needles that are as short as possible. They don't like to insert the needle too much. They cannot hit some vital structures such as blood vessels, and they want also the needle to be as far away as possible from the blood vessels to avoid complications. And the way this is usually planned is by infecting orthogonal MRI slices, and they select like some path for the needle, and after that they observe like many slices that are orthogonal to that path, and just check the needle is far away from vessels and other things like that. Okay, it is a tedious process for the neurosurgeon. They try to avoid it. They actually, even though planning is fundamental, it's important, cannot be avoided. They don't like to do that. They don't get paid for that, and they rather take whatever they can for the operating room and do it in progress.
I don't understand. Shorter pathways, shorter farther pathways.
Yeah, like this is the middle, and like they want each line to be as short as possible. Okay,
but it says farther pathways.
Yeah, okay. Farther in terms of proximity, they want the needle to be far away as possible from the vessel. Okay. And alright. So they use like MRI slides, like I said, for planning. Like recently, the grid map has been proposed to ease some of the detection and help the neurosurgeon to pick where to insert the needle. And the images you show there, some visualizations of each region. Here we only consider the length and the proximity. I just explained it. And on these grid maps, the black region are regions if the needle is inserted there, that is going to be a vessel, and that is going to like severely harm the patient. And blue regions are safer than red regions. Okay? And the idea is neurosurgeon use this information to plan the insertion of the needle. And we want to be able to use this thing inside the operating room to draw the, okay? And one of the obstacles to do that is achieving interactive rates, real-time rates for the computation of the frequencies, like being able to get image on the fly and compute the frequencies on the operating room. That's the problem we deal with here. And previous methods for computing the arrangement, they are far away from interactive rates, or they actually interactive rates for really for low resolution representations of like whatever structures are involved in the procedure. And our base work is a work from a lab mate, and the computational framework we propose for computing the race maps is naive, and computing a single race map for a medium-sized mesh, it takes 3 hours. And we actually interactive rate by basically doing two things: using acceleration of structures and using some techniques from our GPU bag of tricks. And the first thing, we represent the white structure, vessels, or surface of the head as meshes we segmented from images, and we embed them into bounding volume hierarchy. And only doing that thing, it's a needle from really huge. You take like several hours and swing the thing, reroute the thing for a couple of seconds, which is here like not interactive on a CPU implementation. Next thing we do is to implement the thing on the GPU. And okay, by implementing the thing on the GPU, we achieve a speed-up order mapping. That's a speed-up comparison between our CPU backend implementation and the GPU implementation. And recording of time, we see that the GPU implementation scales better than the CPU implementation when we increase the size of the rig. If we consider like more insertion point, yeah, the higher the resolution of the arrangement, the higher the speed of your thing. And okay, this is not the only thing we try for the GPU implementation. We did some load balancing on the GPU to maximize the use of GPU cores. And okay, by trying like meshes of different resolution, we observe that we can get time reduction of up to like 30%. Like this line right here is for a binary structural mesh, for a mesh for the record that is like really large. And at this point, I mean, it seems to me like a root clear the application becomes memory bound, and the speed of just, I mean, no matter how big our binary structural mesh, it doesn't get any better than that 1.4x speed up. And okay, we compare our formulation of the arithmetic computation with the factor reported alternative method for computing the arithmetic. And the formulation is kind of different from ours. We get meshes and we segment images and construct meshes, and they work directly on the volumetric data. And okay, for like one mesh, we right, this right here is the voxel-based method, and this right here is our method. And it's not only faster, but it scales much better to the size of the problem. And okay, so we are able to compute the arithmetic like a really fast rate, okay? But then, okay, what kind of thing can we do there with that framework inside the operating room? We enable things like target repositioning and controlling the speed of the needle. Like on the operating room on the fly, the surgeon can adjust the position of the target and the insertion point also. And okay, he can move the target point and observe the effect that has on the rate map. And okay, that's good to kind of compensate for maybe tissue shifting and other things that may happen during the intervention. And yeah, another thing is the surgeon has to do the same thing with the insertion point, and he needs to pick one target point in like some region. And that's actually not an easy thing, and we enable guided target repositioning for that thing. Like for this region of interest, like this right here is like a green showing the minimum risk that can be achieved if the target is positioned near that area, and that thing can be used by the neurosurgeon to reposition the target. We actually did an experiment to see like it's pretty fast. I mean, this is really useful. We did an experiment to show that we had to treat one treatment in which the subject had to just position the target like without information from the arrangement, just like visual guidance. He only could see like something like this, and absolutely no information. Right. And the other treatment was with the guidance map, and we observed that actually, okay, without any guidance, people tend to choose paths that are really far from suboptimal. Okay, and so we want to be able to use the risk map intraoperatively. We have no problem now with if we have achieved interactive rate, real-time rate there, and the next thing will be like figuring out the whole architecture, how to put together the planning tool and the imaging the device for doing the images and the stereotactic framework or something like that, and try to on a clinical scenario. And we can do like many more constraints in the RIC model, and something that came out that getting the feedback from expert neurosurgeon was kind of like using that technique to plan the radiation to treatment with gamma knife, and that's it. Question.
So where are you getting all of your data? What kind of laboratory do you have? Who are you working with?
I got jobs to mention, like they were faculty, like they get them from like NPR or something like that, and yeah,
Who gets them?
I just got data. Like, what do you mean?
Well, where does this data come from?
Like from some hospital, I mean.
Who gets that?
Who's your advisor or lab? Which lab do you work in?
I work on the computer graphic lab. I work for them. So like, where the data come from? Is from like some anonymous patient from like some hospital within Houston.
Could you please, I do not understand, you gain basically a speed advantage, right?
Yeah.
Can you repeat again, what was the trait that helped you gain this speed advantage?
Okay. We avoid brute force approach. Okay, for computing this region right here, we need to like see if the needle intersect the vital structure, okay? And for computing the proximity, we need to find the closest point of like any point in this mesh to this line right here. So we avoid brute force computation by using a VBH. This thing like it's an algorithmic improvement. I mean, it's not computing the risk for one pathway. It's really from linear to logarithmic on the number of both like points and triangles on that mesh. The second thing we implemented on the GPU, and we do like a very efficient traversal VBH that exploits GPU texture memory for caching. Yeah.
So you have basically two takes. One was a hardware trick, the one inside the GPU.
Yeah, one is an algorithm.
And the other was an algorithm.
Yeah.
Can we go back to the algorithm trick?
Yeah.
Can you explain again what was the algorithm trick?
Okay. If I have a mesh and I want to see if like some directed ray intersects that mesh, I have to like test the thing and like every triangle against that thing. If I partition the space, I can avoid like many of those queries. And yeah, we have used a data structure and it's like logarithmic, like making that query logarithmic on the size of the mesh. And we tried like a third thing on the GPU. And the thing is traversing that mesh.
So the algorithm was instead of dealing with the entire thing, basically you split it up into small geometric.
Yeah, we create a hierarchy. Like, okay, the first node is the whole thing, then like it's split in half, and like it's like a tree.
That's why it's logarithmic.
together.
So your results are sensitive to these parameters K1 and K2. So how do you find the best values for that?
That's the thing. That's I mean, it depends on the procedure and it depends on the surgeon's date or whatever. And we no matter. I mean, we try to read like one word. The length is more important than the proximity. One where they are the same, and one and it's three. And in all of them, we observe that people they just plan to walk path. Like if they have people need like some guide. Yeah.
This is very dangerous, right?
What do you mean?
Because you're too close. Proximity is so low, right?
Yeah, like here, yeah, this way right here. Okay, this means that I'm only carrying a length. Like for proximity, there are like some procedures in which you can actually like retract a blood vessel, like move it a little bit. So in some cases, you actually are going to like carry a leg only.
You say you improve digital statistical tests.
Yeah, we like for a t-test, we observe, and for all length was improved in every for like every pair of weight. And on proximity, we only observe a statistical significance here, like here and here. There, we found no evidence of like proximity being improved. But yeah, we
very clear in your presentations.
Yeah, one last question. One before last question. Is there any loss with your algorithm in the quality of the map? Because it's not clear if you compute exactly the same map or it's a different map.
No, there is no. I actually like we can use like higher resolution measures. We can achieve like better accuracy. I think, but like I didn't evaluate that, or that's what I think.
Okay.
Yeah, I actually have a small comment about the computation of the risk map. So if you already have the vital structures in your data, how about you compute the distance field from your vital structures? And then you use the distance field, the gradient of distance field to force the direction of the needle. You will constrain the direction to just some comment.
It sounds like you don't really understand the idea.
Yeah, yeah.
I will go back to the idea. Right?
Okay.
Okay, thanks for the presentation. The next presentation is wind pump. Please speak in 10 minutes, otherwise you're not going to get a chance to have lunch.
Heavy breakfast today, heavy breakfast.
Good morning everyone, my name is Nipun Sugar and today my talk will be on adaptive optics imaging of the optic nerve for early detection of glaucoma. What is glaucoma? Glaucoma is a group of eye diseases that result in the death of ganglion cells and degeneration of axons. The mechanism behind this disease are not fully understood. There is a lot of work that suggests that the initial insult to axons due to increase in intraocular pressure occurs at the level of lamina tubosa. So what is the lamina tubosa? Lamina tubosa is a collagenous beam-like structure that is present in the optic nerve head. This structure provides both functional and structural support to the axon bundles that pass through this structure. In reality, the lamina tubosa is not perfectly tubular, but as you go deeper into the optic nerve head, the whole structure changes. So how does the lamina tubosa look like humans with glaucoma? Quickly, I showed that there is increased cupping and growing of the surface with progression of disease, as you can see in this cross-section images.
To show that we had to treat one treatment in which the subject had to just position the target like without information from the rhythm, just like visual guidance. He only could see like something like this, and absolutely no information. Right. And the other treatment was with the guidance map, and we observed that actually, okay, without any guidance, people tend to choose paths that are really suboptimal. Okay, and so we want to be able to use the risk map intraoperatively. We have no problem now with we have achieved interactive break, real-time break there, and the next thing will be like figuring out the whole architecture, how to put together the planning tool and the imaging the device for the images and the stereotactic framework or something like that, and write a clinical scenario. And we can include like many more constraints in the RIP model, and something that came out by getting the feedback from expert neurosurgeon was kind of like using that technique to plan the radiation to treatment with gamma knife, and question.
So where are you getting all of your data? What kind of laboratory do you have? Who are you working with?
I got just the message. Like they were faculty, like they get it from like NPR or something like that. And yeah,
who gets them?
I just got data. Like, what do you mean?
Where does the data come from?
Like from some hospital, I mean.
Who's your advisor or lab? Which lab do you work in?
I work on the computer graphic lab. I work for them. So like, where the data come from? From like some anonymous patient from like some hospital here in Houston.
Can you please, I do not understand, you gain basically a speed advantage, right?
Yeah.
Can you repeat again what was the trait that helped you gain this speed advantage?
Okay. We avoid brute force approach. Okay, for computing this region right here, we need to like see if the needle intersect the vital structure, okay? And for computing the proximity, we need to find the closest point of like any point in this mesh to this line right here. So we avoid brute force computation by using an EVH. This thing like little algorithmic improvement. I mean, it's not computing the risk for one pathway. It will from linear to logarithmic on the number of both like points and triangles on that mesh. The second thing we implemented on the GPU, and we do like a very efficient traversal of the VVH that exploits GPU texture memory for caching. Yeah.
And you have basically two tricks. One was a hardware trick, you went inside the GPU.
Yeah, one is an algorithm.
And the other was an algorithm.
Yeah.
Can we go back to the algorithm trick?
Yeah.
Can you explain again what was the algorithm trick?
Okay. If I have a mesh and I want to see if like some directed ray intersects that mesh, I have to like test the thing and every triangle against that thing. If I partition the space, I can avoid like many of those queries. And yeah, we have used a data structure and need like logarithm, like making that query logarithmic on the size of the mesh. And we tried like a third thing on the GPUs. And the thing is traversing that mesh.
So yeah, the way it was, instead of dealing with the entire thing, basically you split it up into small geometric.
Yeah, we create a hierarchy. Like, okay, the first node is the whole thing, then like it's split in half, and like it's like a tree.
That's why it's a lot of rhythm.
Yeah,
So your results are sensitive to these parameters K1 and K2. So how do you find the best values for that?
that's the thing. That's I mean, it depends on the procedure and it depends on the surgeon's state or whatever. And we no matter. I mean, we try to read like one word. The length is more important than the proximity. One where they are the same, and one and the three. And in all of them, we observe that people, I mean, they just plan to walk in a path. Like if people need like some guide. Yeah.
This is very dangerous, right?
What do you mean?
Because you're too close. Proximity is so low, right?
Yeah, like here, yeah, this way right here. Okay, this means that I'm only carrying a length. Like for proximity, there are like some procedures in which you can actually like retract a blood vessel, like move it a little bit. So in some cases, you actually are going to like carry a leg only.
You say you improve digital statistical tests?
Yeah, we like for a t-test, we observe, and for all length was improved in every for like every pair of weight. And on proximity, we only observe a statistical significance here, like here and here. There, yeah, we found not evidence of like proximity being improved. But yeah,
so very clear in your presentations. Okay,
Yeah, one last question, one before last question. Is there any loss with your algorithm in the quality of the map? Because it's not clear if you compute exactly the same map or it's a different map.
No, there is no, I actually, like, we can use like higher resolution measures, we can achieve like better accuracy, I think, but like I didn't evaluate that, or that's what I think.
Okay.
Yeah, I actually have a small comment about the computation of the risk map. So if you already have the vital structures in your data, how about you compute the distance field from your vital structures? And then you use the distance field, the gradient of distance field to force the direction of the needle. You will constrain the direction to just some point.
It sounds like you don't really understand the idea.
Yeah, yeah.
I will go back to you about the idea. Right?
Okay.
Okay, thanks for the presentation. The next presentation is green pump. Brandon. Please speak in 10 minutes, otherwise you're not going to get a chance to have lunch.
Heavy breakfast today, heavy breakfast.
Good morning everyone, my name is PhDshowcase and today my talk will be on adaptive optics imaging of the optic nerve for early detection of glaucoma. What is glaucoma? Glaucoma is a group of eye diseases that result in the death of ganglion cells and degeneration of axons. The mechanism behind this disease are not fully understood. There is a lot of work that suggests that the initial incident of axons due to increase in intraocular pressure occurs at the level of lamina tubosa. So what is the lamina tubosa? Lamina tubosa is a collagenous beam-like structure that is present in the optic nerve head. This structure provides both functional and structural support to the axon bundles that pass through this structure. In reality, the the lamina precosa is not perfectly tubular, but as you go deeper into the optic nerve head, the core structure changes. So how does the lamina precosa look like humans with glaucoma? Quickly, I showed that there is increased cupping and growing of the surface with progression of disease, as you can see in this cross-section images. So, to learn more about this disease, I use a monkey model for experimental glaucoma, where one eye is normal and the other eye is induced glaucoma. To induce glaucoma, the trabecular meshwork is treated with an argon laser so that it blocks the flow of the aqueous, thereby increasing intraocular pressure. When the IOP increases, it imparts stress on the lamina precosa surface, resulting in the bowing and thickening of the surface. This could result in change in the geometry and possibly crimping and shearing of the axons. And when you crimp and shear the axons, it will result in loss of signal and permanent blindness. So what have we seen so far? Several researchers have done different imaging modalities in ex vivo as well as in vivo using scanning laser ophthalmoscopy and optical coherence tomography with adaptive optics. My first aim is to see if there is any difference in the lamina precosa pore geometry in left and right eyes of a normal monkey. And the second aim is to track changes of the same structure in eyes with glaucoma. For the first aim in my experiment, we used 6 normal monkeys in the age of 1.5 to 4 years. They are anesthetized. The eyes are dilated and contact lens are used to prevent corneal dehydration. The following data were acquired in every imaging session. The first data is acquired using spectral domain OCT. We acquired 48 B scans at 20 degrees. With this data, we can measure the depth and the growth membrane opening area. The IOL master is used to measure axial length and corneal curvature so that you can convert the pixel units to real physical micron units. And finally, we acquire images of the anterior lamina precosa surface using adaptive optics and ophthalmoscope. So here I am showing an image, a cross-section image of the optic nerve head acquired using an LCD. There are several points marked on this image. The ones that we are interested in are the green and the red ones. The green is the RP, bruised membrane region, and the red is the anterior lamina precosa surface. Second imaging modality we use is the Houston adaptive optics scanning laser ophthalmoscope. So why adaptive optics? Even though we use glasses and contact lenses, there are still some subtle optical imperfections in the eye, which makes it very difficult for the current clinical instruments to get high resolution image at cellular level. So with adaptive optics, we can correct those optical imperfections and image at high resolution, and we can at cellular level. So we use an 840 nanometer laser source, and the wavefront sensor measures the wavefront error, and the control algorithm corrects the aberration by sending voltage to the photometer, and we get high resolution images. The image here at the bottom, if you can see, is an image acquired at 1.5 degrees away from the fovea without adaptive optics. With adaptive optics, you can see that the resolution has improved drastically, and these white circular discs are induced photoreceptors, which is about 4 microns in diameter. So here I have acquired a video of the optic nerve head using AOSLO. Here I am scanning at different depth, starting at the most anterior surface and going deeper and deeper into the optic nerve head. This red line should also move. I'm sorry it is not moving in this video. And at this focus, you can see the pores are in better focus. So once I acquire all the images at different depth, I pick the image which is at best focus on the lamina precosa. And once it's in, you can see that with the adaptive optics, the resolution and contrast has improved drastically between left and right. We compare the SLO and the AOSLO. So once we acquire these images, we do some adaptive thresholding and graphical segmentation to segment the pores and the beams. In cases where these methods didn't work perfectly, we do some manual segmentation also. Once these pores are segmented, we calculate different pore parameters like the area elongation and the nearest measurable distance. And this surface is also transformed into 3D surface by picking a thin space line, the points that were marked on the SGOCT slices. And all the parameters are measured in 3 dimensions. I also do a global and local analysis at different locations in the image, produce some local analysis, the optic nerve end is divided into different sectors, and selected tests are performed on these locations. We performed a two-sample KS test, and we found that the mean pore geometry is similar between the left and right eyes of the normal monkey. We also quantified the cupping, that is the ALCSD, and the gross membrane movement area. The gross membrane movement area is measured by fitting an ellipse to the points at the rim of the optic nerve. That serves as the reference point, because there is a lot of evidence to suggest that even if there is change in disease, this plane remains constant. And we also found there is no significant difference in these two parameters between eyes which are normal. Coming to the first experiment, the laminar pore geometry, the anterior laminar superficial surface depth, and the BMO area genetically similar between fellow eyes and normal monkeys. 50% of the monkeys showed statistical significant spatial distribution of pores based on pore area. That means the pore area is not, there is no, they can be distributed all over the eye. There is no distribution which says that small ones are here and big ones are there. And these values will serve as nominated data for future studies for experimental glaucoma. For my second experiment, the aim is to track changes in the same structure in eyes with glaucoma. For this experiment, we used 5 monkeys which has glaucoma in one eye, 3 to 4 years of age, and before each experiment, the monkey are anesthetized, eyes are dilated, the intraocular pressure is measured before and after each experiment. Pharmacological agent is reduced so that the IOP is reduced, and a contact lens is used to prevent corneal dilatation during imaging. We measure several parameters like axial length and corneal curvature using IOS master. We acquire images of the optic nerve using SDOCT, and the pore elongation, area, and nearest neighborhood distance are measured using this supply using AOS as well. The data shown in this presentation corresponds to data taken at 3 different time points, so that we can do a longitudinal study. That means baseline, follow-up 1, and follow-up 2. Baseline is when is before using glaucoma, and follow-up 1 is the first time we see some change, and follow-up 2 is the latest date to be analyzed. Here you can see images from the same eye at 3 different time points: baseline, follow-up 1, and follow-up 2. You can also notice that the value has changed from 9 millimeter mercury to 25 and 41 at different time points. If I zoom into one of the locations, you can see that there is some change in structure. We have not yet analyzed the data from the glaucoma monkeys, but so far what we have seen is that adaptive optics can be used to track laminar pore geometry over time in glaucoma monkey eyes. My next aim is to correlate these changes, the pore area, orientation, and surface curvature. I would also like to examine the laminar pore geometry so that I can compare ex vivo versus in vivo. I'd like to thank Kevin Ivers, Hope Pinot, Jason Porter, George Lutakis, Ricardo Villalta, and Deepak Chichikalu for their inputs and contributions. Thank you very much.
So you got a name, aim number 1 for which you analyze data, right? And aim number 2, the data analysis is still pending, correct?
Yes. We have only acquired the data. We have not yet.
I'm not clear. I mean, what's the outcome for aim number 1?
Aim number 1
is the null hypothesis holding? Does the alternative hold? I mean,
yes.
What was the bottom line?
So first, why do we do this? Because we acquire images from the same monkey without glaucoma at different time points. It helps us verify our method so that there is no change. So if there is no glaucoma, that means even if I image the same eye at different time points, I should get the same results. The imaging, so that I can see that the imaging is consistent, the methods are consistent.
So, can you repeat again aim number 1?
Aim number 1 is imaging the left and right eye of normal monkeys at several time points, so that we see that the imaging is consistent. The aim number 2 is to do the same thing, but after.
So that was your hypothesis, right?
Yes. The hypothesis.
My question is, did this hypothesis pan out?
Yes, the hypothesis pans out.
Where is the test?
So we did a t-test and a KS test to compare these hypotheses, and the p value is less than 0.05.
And that goes on a sample of 5 animals.
Yes. 6.
6. What are the numbers that are delineated in the red?
They are the ones that we saw some higher changes in core area. Core area, from this what we concluded was that you can see that there is no the main reason maybe why my opinion is that why there could be some higher changes is because when I am comparing at different time locations, we are not able to image the same location. There is some area where in some eyes you can image the small location, and in some eyes you can image small location because of vasculature. Because the vasculature will project a shadow onto the surface, so when we see dark regions. My long-term goal is to see that, so when I'm doing longitudinal study, I'm doing it on a monkey, but for a human eye, we cannot do longitudinal study. The human eye, will come and sit, and we have to decide whether it is glaucoma or not. For that, we are trying to build a model which will predict the progression of the vision.
Okay, thanks, Mr. Fernandez. And the next topic will be lecture video indexing and semantic search by table.
Hello, my name is Tyson Tuna. I am working in the substance of video project with Dr. Shubha, and I am specifically working on lecture video indexing. So let me start with a question. Please raise your hand. How many of you use the lecture video for a class? And how many of you heard of MOOCs, basically online open courses, or Coursera, which is providing lecture videos from Stanford videos and so on.
Can you speak louder?
Yes. So this type of...
Did you ask a question?
Yes.
Can you repeat the question? Because I haven't answered.
I asked how many of you use the lecture video for a class first, and how many of you heard of MOOCs, open online courses, and Coursera, so on, iTunes University of Education. So, as you may notice...
The answer is that some of us have done both.
Yes, yes. And these videos are very commonplace, and delivering coursework online with those videos is very common in YouTube education, as we can see in the MOOCs and Coursera. Thousands of videos in the internet, and people watching these videos millions of times. And there was an interesting news in New York Times that's saying that Coursera is growing faster than Facebook because they have 1.7 million users in just one year. And this type of lecture videos have been used at UFS for a long time. Instructors were using their tablet PC and recording their PowerPoint slides and providing for the students. And some surveys and focus groups interviewed, and based on these surveys results, the videos found powerful and versatile resources. And one of the results from the surveys saying that how people use the videos, most people use either to review the concept before test, or when they didn't understand, they want to read the concept, or so on. So as we can see, these videos not only used for online classes, but also for face-to-face classes as a supplementary document. So the format, the problem is in the format of the video. So if you want to access the content of a video, either you have to scroll from the first second to the end, which mostly those videos are in average in 1 hour. So the ICS video project aims to increase the accessibility with providing this indexing, captioning, and search features. which is, I will talk more about indexing, but search provides quick keywords from inside the video, so people can just direct access those points, and capturing is texting the lecture of the instructor. And those features are integrated in ICS Video Player. Some of you already have used this feature, and these are not index point. So they have timelines, and each image represents an index point and hopefully a different topic. This was our target. And our objective in video indexing is we want to split the video into different segments, and those segments should have different topics. And we want people to be able to access these segments easily. They can switch, so they shouldn't be too many. So if you have 100 index points and people will not be able to find what they are looking for. If it is very less, just a couple of 2, 3, then you may not find still your point of interest. So these are our features for video indexing. And how can we do this? So there are the simplest way. We split the videos into every time interval. Let's say 1 second, 3 seconds, 5 seconds, or 3 minutes and 5 minutes. So this approach is very fast, but may not be suitable if your time interval is small, short, or and as we can, it's very intuitive that there is no topic relationship with those segments. We can use image-based indexing, which means we compare the images. I will talk more detail, but there is also no topic relationship. Well, the other concept is comparing text because we know that topics are defined by the context and text in the video. So in image-based indexing, let's compare these two frames. So when we compare these frames, we know that this pixel is different here from this pixel. So we compare each pixel, and based on image processing, they found different. And in the conceptual, they probably different because they are talking about different story. In the second image, we also have two images, and the pixel-wise comparison, we will see that the pixel difference are high, and they are different images. But as a topic, they are the same topic because it's an explanation. The title is the same, and there are common words. So with text-based indexing, we can catch this similarity. So we have these two images, and we compare those images based on the text. So we have this text and this text. These texts are captured with optical recognition tools from the screenshots. And so we can see that there are a couple of videos, there are a couple of words which is in common, so we think that those are related, so they should be the same topic. So, so we know that videos are repetition of images, and as we can see, if we extract the image from a video, we will see those thousands of frames, and most of them are repeated. So first we need to find out this slide transition. So this is our first step, and we do this by a very straightforward image processing comparison with pixel by pixel. So we see that these images are on my slide transition. And then second step, we want to compare the topics, and we want to merge those slide transitions to index point. So this is what we are really focused on. So when we compare two frames or group of frames, how did we define the topics? How the topics is different? So probably it's so our intuitive idea is different topics mean different words. If these two frames related one topic and these two in another topic, we believe that number of common words used in those two is different than number of common words in those. So this is our first approach. And so when I want to compare this third slide with the left and right group, so how should I decide? How should I compare? What should be my metric? Right? So my metric can be number of common words, percentage of common words, or something just like cosine similarity. So there are lots of other criteria we can use, but we choose cosine similarity with our experiments. It's a very common approach in text mining and machine learning. So how did we use the cosine similarity? So we put the frames, and we count the frames like that. So frame 1 has four words, frame 2 has 2 words and 1 extra new word, which is word 5. So we put them in a vector like a matrix. So when the word exists, so we put 1. If it doesn't exist, we put 0. So we create those vectors. So those are my vector, which is a reference of all words. I will not talk most of the detail in our work, but basically, our objective is we want the topics described at least in a certain of time. So we know that a couple of topics cannot be described in 5 seconds. So we have a time limit. So we check for that. We check the smallest time duration of the slide. Then we try to combine that. So we check the similarity between that current frame to the left and right, and if it is higher than the other one, then we merge that side. And we repeat those steps until we reach a certain threshold. That every frame has a certain threshold length. This is the first phase, and in the second phase, we merge these segments with another threshold, which is a threshold every segment we use, and it is currently 6 minutes to 9 minutes. And evaluation, this type of work has not been done previously, and currently people have been indexing news videos, or people are using text mining for document clustering. But we have another information which is time interval, so it is hard to create the grant truth information. So our approach is we will create a manual index point by instructors, and we will compare our results to those results. And the other is combining short video clips and fine cut clips. Coursera has those type of videos. They divided one lecture video into 5 to 10 minutes video chunks. So we combine them and we try to find those chunks and start of those points. So in the status, these videos, indexed video lectures, indexed lecture videos are very used, and we got very positive feedback from the users. And we implemented this indexing tool, and it's based on cosine similarity, but it will change in the future, but we are still evaluating and doing our tests. And our next future work is creating new algorithms and comparing them, and hopefully with doing more surveys, getting more input from the users, how they are really useful. And hopefully some of these indexing ideas can be carried over the search inside the video. That's my thought.
So from your interesting results, do you think you can get the summarization of the video?
Summarization of video?
Because you have the index point.
Yeah, that's true. Normally, our first aim is to find the cut points, but it's very related to summarization of part. But yeah, we didn't finalize our algorithm, but still, we can even use those vectors as a different attributes for a machine learning algorithm to compare our results. So it's not finalized, but that's a good point. That's very related, and we need to look at that.
If you really come.
Yes.
Yes. It's unclear to me if you can, your algorithms allow searching only within one video, or you can search for a topic among a collection of videos. So
Yes,
for instance, if I'm looking for
about search inside video is available for both inside the video or multiple search. So you can search for a keyword in your class, maybe more than 10 videos for a semester, or even all over the ICS video project database.
That's simple.
If you have the summarization, you can do that. video based.
So regarding your evaluation, which is missing, do you have any plan, timeline about how to go about to do it?
Yes, actually, yeah, I have some slides. Yeah, for example, this is from Coursera videos. So these are video chunks, finding some of them. So we combine them in one video, and then we process in our system. Then try to find those video chunks. And this was text-based indexing. As you can see, we only catch the first part. This is the first part, and it's not even a catches because it's the first one is always indexed. And this is the second part we are working on, and as we can see, we catch more jump points, but this is still not enough. And it's also there are a lot of properties, how the topic is related. So this is the easiest way we can evaluate, but we have an interface for instructors to enter their input, how the videos should be indexed and how do they rate. So hopefully we will do that end of the summer.
Okay, thanks. Next presenter is Ilyas. His topic is interfacing real-time ozone information.
Good afternoon, everybody. My name is Ilyas Yan. My research topic is mobile computing and human-computer interaction. I work under supervision of Professor Pavlidis, and I am here to describe what I did last semester towards my PhD thesis. And I have developed ozone monitoring application which provides real ozone prediction to the mobile devices. Ozone is environmental pollutant developed under certain environmental conditions in big metropolitan areas such as Houston. As all you know, ozone by itself it is dangerous for our health, especially when it enters the ground. It affects our respiratory system and it causes a variety of severe disease. By the way, there is a tidbit information here. Ozone is actually really bad and ranked number 7 in terms of worst ozone polluted cities. Up to now, ozone prediction is static, and we had very gross ozone prediction information. The very well-known application, which is the Weather Channel app, predicts ozone for all day, for entire 24 hours. Let's see what ozone is today. And that is sending this sensor sending data, and then you are seeing current ozone. What it says here? It says ozone is 22, and that is with textual description with black, green. Green for what? For all Houston and Galveston and Brazoria area. That is huge. That is 1,000 square of area. Let's see another example from August. And again, sensor sent the data, and then you see red flag. Red flag is dangerous. I mean, you should keep yourself at home all day, entire day. But that is not the work. That is not the things works practically. And because actually here, since we have only one sensor, and that is the result. I mean, we shouldn't do any more things here. But thanks to technology, we have a network of sensors, and they are sending this data, and then these data are sent to the server, where computational algorithms are applied, and interpolate this data and interface the mobile device, as we did here. And that is like changes minute by minute. And you can track, like, that is exactly the same day that I just shown from the Weather Channel application. Okay, that is red, but red where? In the middle of downtown, not Galveston area. And not for whole day. that is dynamic information, which we call spatial temporal data. However, that is not easy. That is not easy to during the design process. We have difficulties. Actually, this project is given by geoscientists to us, but we have fight each other. I mean, big fight. They wanted this design, and we wanted this design. They wanted this design because they wanted to treat this dynamic information as we collect it through environmental sensor networks, and they wanted to behave this static information as dynamic information as static information. But you see, it's like a flag system here. It is just coloring, even though there is no ozone alert. But what we suggested here, we approach the ozone data, ozone dynamic data as a radar style, and display it like a radar style, and you see the visibility, and you can see how it moves. If there is no divergence, there is nothing to show, as we did here. We understand this principle because geoscientists, I hope we are all computer scientists here. Geoscientists, they don't know they don't know very well human-computer interaction design principles. But unfortunately, we couldn't. Unfortunately, there was no agreement between us. They was forcing us to implement this one, but we keep telling, okay, we should implement this one. Then what we did, we took survey. We took our thought to user and see what they reply. We got 51 participants. We got 31 participants, and they responded the following questions. Actually, first and second question is so important for us because those questions are exactly related to design style. Which preferences they like, radar style or flag style. The rest of the question is just supporting the first and second question. Okay, that is the point actually you want to see. But we also surprised. User also split as like we did, like geoscientists versus computer scientists. And that is how things works in human-computer interaction if you work this area. And what we did to approach that problem, we gave these both options, whatever user likes, radar style or flag style. But the thing is, like all habits are hard to die, bearing in mind there is a historical analogy here. Like as you all know, people were riding, all centuries people were riding horse on the left side. Why? Because there is a logic behind it. That is unshielding sword and defending themselves. That is easy. That's why they choose to drive on the left side. But once car technology comes, the things has been changed. And because most of the people, they are right-sided rather than left-sided, then they change the habits to the way like driving the car on the right side. But again, bottom line, habits are hard to die. That's why we have this still dispute happens many years. They start English style with this way, and all the rest of the words they use this way. Again, in our case, that is the flag system. You see, you have seen the weather channel app, and we wanted this side. We argued with this side or this side, but we gave this both option to user. There is like a historical deja vu in a small case it happened in front of our eyes, and this research gives me in-depth study how something it is different than you thought. Since we approach problem very deeply, very thorough process actually, and I released this app on the App Store. It's free to download since December 10th, 2012. And so far, over 1,000 downloaded. People were riding, all centuries, people were riding horse on the left side. Why? Because there is a logic behind it. That is unshielding sword and defending themselves. That is easy. That's why they choose to drive on the left side. But once car technology comes, the things has been changed. And because most of the people, they are right-sided rather than left-sided, then they change the habits to the way like driving the car on the right side. But again, bottom line, habits are hard to die. That's why we have this still dispute happens many years. They start English start with this way, and all the rest of the world they use this way. Again, in our case, that is the flag system. You see, you have seen the weather channel app, and we wanted this side. I mean, we argued with this side or this side, but we gave this both option to use it. There is like a historical deja vu in a small case involving I mean, it happens in front of our eyes, and I mean, this research gives me in-depth study how something it is different than you thought. Since we approach this problem very deeply, very thoroughly, and that is a success actually. And I released this app on the App Store. It's free to download since December 10th, 2012, and so far over 1,000 downloaded. And surprisingly, within 2 months, even though there are lots of air quality applications, we are now number 9, and we are hoping it's going to be number 1st with your help. And we got a couple of feedbacks from the user, as you see here. Thank you. Any questions? Yes.
Yeah, the problem with volunteers is that it doesn't give you a truly random sample.
Actually, we ask also for the supported question. We ask them like whether or not they are following the weather application. I mean, weather application. I mean, that is how we can. I mean, there is no way. I mean, once you give anonymous survey, I mean, that is the way you have to approach the problem. You have to get feedback and see with supported question as well. I mean, we also gave like whether or not they are using weather application or they are looking pollutant, air quality prediction. That is all supported first and second question. That's why we ask this question.
No, I understand the questions you ask, but the point is that you don't have a truly random sample because people are volunteering. It is not a random sample. A better way would be to, identify a random sample.
Actually, we gave random sample. I mean, we sent this survey through UH community. That is random. I mean, we didn't pick like subject randomly. I mean, like selectively. We gave this survey throughout like UH email.
And then 51 people.
51 response.
How many did you send out?
I mean, we sent like, for example, CS grad UH interview.
Right. So what's the population approximately that you were targeting?
I mean, let's say like around 200 or 300. Yes.
Are there more interfaces? I mean, to see the phone, or why did you compare only these two?
If you download this application, there are more settings, and there are.
So, but why did you choose these two? One is yours and one is an existing.
There is no other options, no other style. If you have your style, and you are welcome to provide your style, and then we can implement and see maybe your style.
All right.
Awesome, man. Again, guys. Please download and provide feedbacks. And we are still open.
Okay, thanks, Mr. Miani's presentation. And next presenter
morning. My name is Su-Jin Wang from Deep Mining Machine Learning Group, and my advisor is Dr. Ai. And my actual topic of today is a polygon-based casting and analysis framework for mining a spatial data set. Here's the outline of my presentation. First, I'll give a general introduction about my research in spatial data mining, and then I will introduce the architecture of our framework, and I will pick up two technologies that we use in our framework, and then to explain the experimental result. And at the end, I will discuss the conclusions and the future work. My research focuses on spatial data mining in general. And spatial data mining is the process of analyzing and discover interesting and useful patterns, associations, and relationships from the large spatial data sets. The object in spatial data sets not only contains the traditional numeric and category data, it also contains the spatial attributes, for example, the latitude and longitude. And there are the two examples that pick up from our case study data set. That's also about Autumn population. We have the latitude, longitude, that's the location information. We have the time information, day and time. We also have other meteorology data like the outdoor temperature, solar radiation, and wind speed. And there are three types of spatial objects: the point objects, the trajectories, and the polygons. Okay, the countries, or the cities, or the blocks, or even the ozone pollution hotspots could be represented by polygons. And our framework will focus on polygons. And spatial data mining is a challenging task. There are several reasons. Okay, for example, the complexity of the spatial data types, the spatial relationships, and the spatial autocorrelations. So the traditional algorithm technique will not work directly for spatial data sets and will work for the spatial polygons. So that's why my research goal is first to develop a new distance functions for the polygons and new spatial classing algorithms so that we can cluster the spatial polygons. And then after that, I will also implement the new post-classing techniques to help the domain experts to extract interesting patterns and generate summarizes. And here's the architecture of our framework. We first download the ozone pollution data set from the GCEQ website, and then we use our controlling algorithm called control density-based classing algorithm to generate the polygons from the point spatial data sets. Because each polygon right here will be representing a ozone pollution hotspot, and then we'll apply our poly-SNN, this is the density-based spatial clustering algorithm, so that we'll be able to cluster polygons into different clusters. And then the output will be, we call it microcluster, dense clusters of polygons. And then we apply our post-clustering techniques. Those techniques will have the plug-in reward functions that capture the locations of the interest list by our domain experts, and then we can extract interesting patterns and generate summarizes for the domain experts. And due to the time limitation, I'm only focusing on the two techniques that we use in our framework. That's the post-clustering technique. The purpose of the first post-clustering technique is going to select a set of polygons from the meta clusters, and so that the sum of the reward of each polygon is maximized, because the domain experts may have different interests and they have different reward functions. Right? And there's three constitutions to these optimization problems. The first one provides two polygons that are especially too close to each other to be selected at the same time. And the second one will guarantee that all the polygons that we selected must have a higher reward function than this right hood. And the third one will guarantee that only one polygon from one cluster to be selected. I'll give an example later when we introduce the experimental result. Now that's the second post-clustering technique that we use in our framework. The purpose of the second one is trying to provide auto-screening techniques that be able to select the clusters with unexpected distribution. For example, we can select clusters whose mean value is significantly different from the mean value of the entire data set based on a single non-continuous spatial variable, for example, the wind speed or either the solar radiation. Okay, and this at the same time, the variances of this selected clusters is relatively small. Now here's the meta cluster generated by our framework. So actually, this polygon here represents ozone pollution hotspots, and this latitude. This map actually shows the Houston-Galveston area similar to Traverse presenters. That's the same right here. And our school is kind of like here. We already know that the ozone pollution in Houston is really bad. Yeah, that's why. And then this polygon we have right here represents the average ozone pollution higher than the EPA standard. That's 75 ppb. And that will be the input for our post-blasting techniques. Now here's an example of one of our results from the first post-processing techniques. In this case, the domain experts may be interested in trying to find the possible maxing areas affected by the ozone pollution. So in this case, we take up the area of the polygons as our first, as one of the reward functions. So in that case, we take up the polygons whose has the maximum areas, but they are not close to each other, and they have the and here's the result. We also have the summarized information for these selected polygons. And here is a small polygon inside the bigger one. Here, that's the whole inside polygon. So our algorithm can handle overlapping polygons and can also handle the polygon with host inside. Now, this is the result of the second post-processing analysis. So in this case, we're trying to find clusters of polygons whose mean value is significantly different from the mean value of the whole data set. And this time we'll take up the solar radiation as the non-continuous, continuous non-spatial variable. And we have 3 clusters taken, and those means that these clusters either happens when the solar radiation is extremely slow or extremely high compared to the whole data set. And the variations of these 3 clusters is relatively slow compared to all the other clusters that we have. And for conclusions, our framework can effectively cluster special polygons, especially polygons, overlapping polygons, and polygons with host inside. And then similar size, state, and locations in our post-blasting techniques can generate interesting patterns and generate summarized information for our domain experts. And I'm currently working on the spatial tempo processing algorithm and try to embed it in our framework. And later I will working on the spatial tempo. Later I will working on the chance analysis techniques to identify the spatial tempo chance over the spatial date. And then later on we can evaluate our framework in more challenging scenarios, not only the audience data sets. And here's the list of publications that summarize my research in more details. If you're interested, feel free to read it up. And that's all. Thank you for your attention. Any questions?
In your algorithm, how do you get the polygons in the first place? Because I think the quality of your clusters may depend on the quality of the polygons in the first place.
Very good question. We first download the data set from the TCEQ, Texas Committee Environment Quality, and they have the point data set. They have the ozone pollution information, and then we use our decontrol algorithm to estimate. They only have like 44 monitor stations among Houston, Galveston area, so we have the decontrol algorithm has the decontrol algorithm will estimate the ozone concentration on this map, on this longitude map, and then we use this algorithm to generate our polygons. And we all actually draw the boundaries based on this. Actually, we pick up the areas with the ozone concentration higher than the standard, like 75 ppb. We just estimate this on like Gauss dispersion. We estimate the ozone pollutions, ozone concentrations at each point, discrete point on this map. So, any other questions?
So how do you get the meta-clustering in one?
Oh, very good. We first get a cluster. This is the the first step we get is just a set of polygons that do not have this color, because each color here represents one cluster. And then we have our distance functions for the polygons, like overlapping polygons. We have our we call it hybrid distance function, so we can calculate the similarities between each polygon here, and then we plug those distance metrics into our polygon-based shared news neighbor clustering algorithm. It's kind of like a density-based clustering algorithm, so we can cluster them into different clusters.
So that's what you call meta-clusters.
Yes, then this is actually one of the subset of our meta-clusters.
Presentation. We welcome our last presenter, Evan Wesley. And his topic is combining physiology with observation in human studies.
Hello everyone. Like last year, PhD showcase, again the last student in year and lunch. So hopefully I will make it on time. And let me close. Hi, my name is Avinash Wesley, and my advisor is Dr. Paulidis. And in today's research, I will be emphasizing on the importance of observation, which is studying the facial expressions in stress studies. Usually, what happens is physiology and observations are studied in isolation from each other. And so what I've done is I brought observation back in the picture and juxtaposed it next to physiology to give a more informed analysis in stress studies. So stress is a very loaded term, and I will define stress as the ever-present physiological mechanism that helps us to cope with realistic challenges or threats, or even perceived challenges or threats. So what happens is whenever there is a stimulus, the sympathetic mechanism triggers signals to the adrenergic and the cholinergic receptors. The former affects the cardiovascular operations, and the later activates sweat glands on fingers and paranasal area. For our, in our lab, we focus on the cholinergic receptors, and for a while, stress has been suspected to play a key role in modulating human performance. And in earlier 20th century, Rios and Dodson postulated the famous hypothesis which related stress to human performance. And in simple terms, it is that too much of a stress or too little of a stress is detrimental to human performance. So qualitatively, it looks like it's common sense, but quantifying it is rather difficult. Well, fortunately, it can be quantified because of its physiological manifestation. However, if there is a physiological arousal, that doesn't necessarily mean that a person is in distress or there is a negative stress. The physiological arousals can happen even when the person is smiling or there is a eustress, positive stress. So we see that the physiology responds the same way. And this is where my research comes into picture, that I combine physiology with observation to disambiguate stress into its types. Now, stress is best studied when it is naturally generated. And for a stress experiment, we focused on surgical training, which is a typical example of a stress training tasking. And we use thermal cameras and the visual camera to record the surgeons while they were performing the laparoscopic skills. And our surgeon pool was experts and novices. Now, in any realistic scenario or experiment where we can do stress studies, ubiquitous way of computing stress is very important. So Dr. Shastri from the computational physiology lab, he developed the perspiration extraction method, which extracts perspiration in thermal imagery. And here we see that method is applied on the maxillary area, and we see the signal perspiration volume. And just analyzing this physiological signals, we found that the novice surgeons perspired more than the experienced surgeons, and this was statistically significant. But as important as this method is, which quantified stress, it was uninformed as to what type of stress it was. And so what I did was, separately from the perspiration signals, I went into observation and I started observing these surgeons. And I took the traditional way of manually annotating these facial expressions. And here is a fellow psychologist doing the
But
same
there
thing
is a
that I did.
drawback. It cannot be rushed under any circumstances.
It can take you up to 3 hours to code 1 unit of behavior. And we found that we can't have our coders doing more than maybe 2 hours a day.
So this manual annotation of facial expressions was very labor intensive, and there was an expertise required. So I took my certification in FACT, which is facial action coding system. It's the gold standard in this field. And it took me around 2,000 hours to annotate all these 1,000 videos from the stress experiment. And just, and this is some of the visualization examples of the facial expressions we made. And these are some of the results of just the observation. I found that the positive expressions were very rare, and they were mostly made by experienced surgeons. While on the other hand, the negative expressions were quite frequent, and the novices exhibited them more, significantly more than the experienced surgeons. Then I used my observation data, and I segmented my physiological signals into distress signals. Like here, we see the red line is when they're actually making negative expressions, and I use that to dissect my signals, physiological signals. And the results that I found was, for distress, negative signals, instances, the novices have more distress than the experienced surgeons. And again, this result was statistically significant. These results are quite similar to what we saw before with the uninformed physiological alone method, but nonetheless, this is more informed through the negative stress. Then now, since in this field, and this work, by the way, won Best Poster Award in National Center for Human Performance. And and this research was actually a subset of a bigger research which was on human performance in a dexterous tasking, which was published in Nature journal. I was then intrigued that since we are already doing physiology in thermal imagery, and we cannot do away with physiology in such stress studies, and can I do my observations in thermal imagery? And by the way, it has its own advantages. That is, he is affected by illumination, lighting conditions, and skin tone. And also the benefit of the contrast that I see in the areas of the face where there is sharp contrast. And these areas, for example, these trackers that I've placed in these 7 regions are very important for emotional expressions. And here we see the contrast that is, thankfully, because of the thermal imagery. For example, the ROI1 on top left, in the eyebrow region, we see the colder eyebrow with contrast to the surrounding hotter skin tissue. So this made the tracker quite robust. And what I did was, each of these trackers were abstracted by their centroids, and then they were tracked over the period of time and forming a trajectory. And then monitoring these trackers, I found my feature vector. And here on the right on top, we see the evolving Euclidean distances of tracker 1 and tracker 6 from the tracker 5. So here, just for the visualization purpose, I've shown 3 trackers instead of 7 trackers. But here we see the evolving distances, and then I computed the standard deviation from the onset to the offset of each expression. And that was my feature vector, the standard deviations. These standard deviations are basically indicators of the muscle action that is happening. And then I feed it into my multilayer perceptron and use tenfold cross validation. And then I used my method on the stress data, and these were the results that I found. It was 81%. So it's not perfect yet, but for the first cut, it's not bad. and I will be improving it, and that will be the end of my PhD. And the broader implication, the broader conceptualization of this was not just from stress studies, but to human studies was presented in GUIDE, and my algorithm was presented in ISBC. So to summarize it, I will use one specific case. Stage 1 was when we adjusted physiological signals and we saw there was arousal. But stage 2 now, with the help of observation, we could see this arousal was eustress. But now, in stage 3, we can actually automate it, so psychologists don't have to do it manually. Thank you.
So did you do a comparison of the automatic method with the manual?
The automated method with the manual, yeah. Actually, the ground truth was what I did.
The manual.
Manual, so it paid off in long run.
So you're 80% with respect to this ground.
Right.
Okay, I think that's all the presentation. And before we go to lunch, I think Leon has 1 minute to talk about the graduate association.
Hello everyone, I'm Beran, and as you may know, I'm not a fan of talking so much, so I don't take your time too much. So, through this event, we have been listening to people in different areas of computer science, like computer architecture, computer vision, data mining, and there are other things, but there is a main point that I wanted to talk about today, that it's good to not forget and take this message for home from this time. And that is through this research that is done in these years, and the PhDshowcase is a measurement of that, is that the department is growing through the month. So the PhDshowcase works as a checkpoint or as a measurement that we can show your results and collaborate with each other. The unique voice of the department is the basic thing that the Graduate Student Association have been based on. So we are, the common thing that all students have here is the passion of research, not the research topic. So what we are planning to is just, based on this unique voice, we are going to build our dreams and improve the department and improve the collaboration between the research laboratories and students and the department staff. So what we are going to do is not just forcing you to join the GSA, or even we are not going to inspire you for that. The only thing that we are going to do is work as a mirror, so we can make this happen and make these dreams happen. So there are three things that usually stops people from collaborating with each other in the department. The first thing is focusing on disagreements. So instead of finding the common things that all of us agree and moving one step forward, we may focus on disagreement. The other thing is taking into consideration the personal ego and the personal motivation instead of improving the whole department. And the other thing is worrying about the wrong decisions instead of just choosing one and moving forward. At the end, I want to thank Dr. Gabriel, Dr. Sopla, and the people from GSA who have worked a lot for this PhD showcase and make this happen. Usually they're saying that the cook is the person who takes the least joy of the meal. But anyway, I would like to thank everyone for this. And please join us and give us your ideas for the GSA. Thank you.